So we'll start here with some gas particles, and if you notice, we have a temperature 300 Kelvin, pressure maintained right around 4 atmosphere, and we have this enclosed box. The first thing we want to look at is if we change the volume, what happens to the pressure? And for this scenario, I want to keep the temperature constant. If we decrease the volume, the pressure increases. Decrease a little more, pressure increases. If we had to put a name to this, we would call this Boyle's law, where the pressure and volume are inversely proportional. If we look at two other variables, let's say temperature and volume, we're going to keep the pressure constant. If we go ahead and change volume, as the volume decreases, the temperature decreases. Go ahead and open that up. Okay, and we are maintaining constant pressure, 4.9 atmospheres, 4.9 atmospheres. Many of you know this when temperature is directly proportional to volume. Many of you know this as Charles' law. The next two variables we want to look at are pressure and temperature. So we'll keep the volume constant, and if we go ahead and heat this up, we'll notice that the temperature goes up and the pressure goes up. One more time, heat that up, the temperature goes up, the pressure goes up. The same thing if we cool it down, the temperature goes down as the pressure goes down. This correlation with pressure directly proportional to temperature is often referred to as Gay-Lussac's law. Now, there are some other interesting things that can happen with this. If we go ahead and keep the temperature constant, and we want to keep the pressure constant also, so I'm going to keep that right around, looks like maybe 4 atmospheres. Let me go ahead and add a few more particles here. Let's keep that right, yeah, that's about 10 atmospheres. So if we keep it at 10 atmospheres, keep it at 216 Kelvin, if we go ahead and increase the number of particles while trying to maintain the same pressure, pump this a couple times, notice the pressure goes up, but if we need to get back to 10 atmospheres, we need to increase the volume. So, as you increase the number of particles, the volume has to increase in order to maintain temperature and pressure. This is referred to as Avogadro's law, where volume and number of particles are directly proportional. If we want to do the same thing, except we want to see how pressure changes with the number of particles, let's go ahead and get this back. And what we're just going to do is we're just going to increase the number of particles and see what happens to the pressure. More particles, more pressure, maintaining that temperature. And this is interesting because this is known as diver's law. So a diver will look at their pressure gauge to recognize the number of oxygen particles that are in their tank. So pressure is directly proportional to the number of particles. Now there is one more. If we go ahead and keep volume constant, and if we want to keep that pressure constant, let's go ahead and get rid of some of these particles. Let's get a few particles in there. Again, let's keep that volume constant. We want to keep the pressure constant. So we'll maintain right around 2 to 3 atmospheres. If we increase that number, but we want to maintain that atmosphere, we need to cool it down. We need to stop those interactions with the wall. And we need to get down to, what was that, 2 atmospheres. So let's get really far, cool that way down. 2 to 3 atmospheres. So as the number of particles increase, if we maintain pressure and volume, then the temperature decreases. This is an inverse relationship between number of particles and temperature. This is called the no-name law. It's just understood. No one really gathered data to have it named after them.